Hello, everyone. Welcome to the final talk of the year. It's a great shame that this couldn't happen in person as previously planned. Regardless, I think we can still expect an amazing talk by Professor Rob Fender from the University of Oxford. The talk tonight is titled Relativistic Jets from Black Holes, Connections to Gravitational Waves and Neutrinos. Let's hear a short introduction about our speaker before we begin. Professor Rob Fender is currently Head of Astrophysics Subdepartment within the broader Department of Physics at the University of Oxford. His particular research interests are in the area of accretion and feedback around relativistic objects, most advanced via observations with radio telescopes such as EMILA, eMerlin, and Meerkat, as well as targeted studies. He is also involved in a wide field commensal searches for radio transients. Previously, he was Professor of Physics at the University of Southampton, and prior to that, the Universitair Hoofddocent at the Universiteit van Amsterdam. He has been a visiting professor at the University of Grenoble, and since 2010, hold a position as a visiting Scar Professor at the University of Cape Town. Amongst other highlights, he led the national collaboration via which the UK joined the LOFAR project, was awarded in 2011 an ERC Advanced Investigator Grant, was chair of the SCAR Transient Science Working Group, and was awarded the 2020 Herschel Medal of the Royal Astronomical Society for investigations of outstanding merits in observational astrophysics, mainly in recognition of his work on accretion around black holes and the connections to relativistic jets. He is also a recipient of the Philip Lieberbaum Prize, a Marie Curie Fellowship, an NWO-VD Prize, and a Lieberbaum's Senior Research Fellowship. In 2021, he became the co-lead of the Next Generation Event Horizon Telescope Working Group on Astrophysical Transients. Now, without further ado, Professor Rob Fender, please.
Thank you very much for that kind introduction. So let me apologize again for the fact that I wasn't able to join you in person tonight. It would have been very enjoyable to come over to Cambridge and give this talk, but I hope I can give you a lot of the flavor of this research via Zoom in any case. So my talk today is going to be on relativistic jets from black holes, connections to gravitational waves and neutrinos. My own research focuses largely, although not exclusively, on studies of relativistic jets from black holes, and what we find is that these are pretty ubiquitous in the universe whenever we have black holes accreting at high rates, something I'll come to in a moment. And in recent years, in the last sort of 5, 6, 7 years, this new field of multi-messenger astronomy has opened up, in which we're combining electromagnetic observations of phenomena such as black holes and jets with messengers which are not electromagnetic waves. So, for example, both gravitational waves and direct detection of neutrinos. Let me start by just saying a little bit about black holes, because I think it's always worth stopping and thinking about what we mean when we're talking about black holes. And so I've been working on black holes for 30 years or so, and you know, we all become rather blasé about it. It's like, oh, we found a new black hole, or there are this many black holes in our galaxy, or M87 is a 6 billion solar mass black hole. But they're truly remarkable objects, and you know, we really should stop and think about them just for a moment. So there's a beautiful quote here by Nobel laureate Kip Thorne. Why are black holes so different from all other objects in the macroscopic universe? Why are they and they alone so elegantly simple? If I knew the answer, it would probably tell me something very deep about the nature of physical laws, but I don't. And the point he was making there is that the largest black holes, and as you know, this is the Event Horizon Telescope image of M87, one of the most massive black holes we know. These black holes are larger than our solar system, and yet, if classical general relativity is correct, their properties are entirely determined by 3 numbers: their mass, their spin, and their charge. What's more, even we don't need 3, because, you know, macroscopically in the universe, pretty much everything is neutralized electrically. So this object, which is larger than our entire solar system, is entirely and precisely, and all the space-time around it, described by just 2 numbers, its mass and its spin. So in this sense, massive black holes are macroscopic objects, sometimes immensely large objects, which are essentially as simple as subatomic particles. You need no more information to describe M87. keeping aside for the moment the accretion flow around it, the black hole itself, you need no more information to describe it than you do an electron. And just to put this in context, this is actually approximately to scale. This is the M87 Event Horizon Telescope image, as I mentioned, probably the first more or less direct image of the event horizon of a black hole, a quite remarkable achievement. And this is the size of the orbit of Pluto. Now, I know, like everybody else does, that Pluto is no longer considered to be a planet, but we still, I think many of us mentally think of Pluto as a kind of marker of the outer bounds of the solar system, which we can conceptualize in our head. And the event horizon of M87 is about 9 light hours across, and Pluto is about 5 light hours from the sun. So in fact, you can see that this huge subatomic particle is, you know, considerably larger than the orbit of Pluto. So let's always bear in mind that we are talking about objects which are like nothing else in the entire universe. They are extraordinarily simple. I'm going to give you a very brief history on black holes just in a couple of slides because I think it's very interesting. So I'll start off with the statement that in 1783, the Reverend John Mitchell proposed stars so massive that light could not escape. Now, about 15 years ago, I gave a talk with this slide in at the University of Grenoble when I was there as a visiting professor. And to my surprise, at the very first slide, this one, the whole audience was in uproar. And that is because in France, they are taught that black holes were not discovered or first conceived by the Reverend John Mitchell at all, but by the famous philosopher and mathematician Pierre Laplace. So now I'm careful to mention both of them in the slide. And the idea was that at the time Newton had this corpuscular model of light, that light was essentially, you know, particles. There are measurements of the speed of light, and Mitchell proposed that if you had a star of more than about 500 solar masses, which actually, as we know these days, is not entirely unreasonable for the early universe, then it would have an escape velocity greater than the speed of light. Okay, and this is not very dissimilar from the reasoning that we use these days to think about black holes. Mitchell's writings were largely forgotten until the 1970s when they were rediscovered. Jumping from Mitchell to the present in a number of discrete and somewhat randomly chosen steps then. So in the 1800s, the wave treatment of light by Maxwell sort of rendered relatively absurd the idea that gravity could affect light. Of course, gravity can only affect massive particles. Light was just a wave. Obviously, light wouldn't be affected by gravity, and no one really considered this for a while. And then, of course, in the early part of the 20th century, Einstein came out with general relativity. Within a few months of Einstein's general relativity being published, Karl Schwarzschild, who was an officer in the German army, this is of course during World War I, worked out the metric for a non-rotating black hole. And we now refer to this as the Schwarzschild metric, and we refer to non-rotating black holes as Schwarzschild black holes. Yes, he managed to do this within a few months, and unfortunately, within about a year or so, he was actually, he had died during World War I, but he had immediately seen that you could have a solution for a non-rotating black hole. In the 1960s, around the same time, the 1960s were a great period of discovery and investigation in general relativity and high energy astrophysics. Pulsars were discovered in 1967. Around the same time, John Wheeler coined the phrase black hole. And again, this caused outrage in France because the expression trou noir was not considered to be a very nice thing to say in polite company. But the phrase has stuck. And there were the first observational hints that black holes may exist. And those first observational hints actually came from studying stellar mass black holes in binary systems in our own galaxy. And these are a particular type of binary system that we call X-ray binaries. And of course, pulsars themselves led to the Nobel Prizes, both in 1974 and 1993. In 1990, Stephen Hawking conceded a bet with Kip Thorne that the binary system Cygnus X1 contained a black hole. Now, both Stephen Hawking and Kip Thorne wanted black holes to exist, so this was a bet which was simply made as an insurance policy by Stephen Hawking in the event that black holes, turned out disappointingly not to exist. Then he would at least get some minor compensation prize. Of course, we're now in a real golden age of black hole research. So in 2015, pretty extraordinarily, I'll have to say, after many decades of trying, gravitational waves were detected from merging black holes. Not only were gravitational waves detected from merging black holes, but this was the first ever direct detection of black holes with masses around 20 or 30 solar masses. So this was a real bonanza, and this led to the Nobel Prize in 2017. In 2017 itself, and this is something I'll come to later in this talk, another type of gravitational wave source that is from two merging neutron stars was discovered. Of course, in 2019, we had those beautiful direct images of the event horizon of M87. And then in 2020, just a year and a bit ago, there was another Nobel Prize for black holes, and that was on the largely for the determination of the orbits of stars around the black hole at the center of our own galaxy. Just some nice pictures to start with. Here's a picture of Jocelyn Bell-Burnell in Cambridge. This is over at the Lord's Bridge Observatory, which is not far from you as you are there right now. And she discovered pulsars in 1967 whilst doing a PhD, and that led to lots of breakthroughs in high energy astrophysics and general relativity. And of course, she was awarded the Physics Breakthrough Prize in 2018, which I'm sure you all know. This is a prize of more than $1 million. She generously donated the entire lot, 100% of it, to the IOP to fund studentships for people from underrepresented backgrounds. This is the bet between Stephen Hawking and Kip Thorne, which was written in 1974 and was conceded by Hawking in 1990. Whereas Stephen Hawking has such a large investment in general relativity and black holes and desires an insurance policy, and whereas Kip Thorne likes to live dangerously without an insurance policy, therefore, it be resolved that Stephen Hawking bets 1 year's subscription to Penthouse. Now, when I'm giving talks to the general public, I point out to the younger people in the audience that this is Architecture magazine, as against Kip Thorne's wager of 4 years subscription to Private Eye that Cygnus X1 does not contain a black hole of mass above the Chandrasekhar limit. And in fact, by 1990, there was overwhelming evidence that it did, and Kip Thorne conceded the bet. And there's a number of famous signatures, witnesses to this bet, in fact, Anna Zitkov and Werner Israel amongst them. So what is a black hole then? So a black hole in classical general relativity, as I'm sure you know, as you're members of an astronomy society, it's a region of space from within which no signal can escape. In other words, you reach a density in the matter where in classical general relativity, the escape velocity at some point exceeds the speed of light. And in fact, once you've passed that point, there is there's a point of no return. There is no other known classical physical forces which can stop the collapse. So you have a problem in a sense, which is that all of the matter collapses to a single point at the center of the black hole, a singularity. We know of no forces once you've essentially gone past being a neutron star. So if I take a neutron star and I compress it by about a factor of 2, it'll start collapsing and nothing will stop it. So there's a singularity at the center. We know that general relativity must break down at the singularity because you're essentially dividing by 0 there, and it's a classical theory. So then, you know, the doorway to new physics, the doorway probably to some kind of quantum gravity is there, but we can't see it because it's already past the point at which the escape velocity from that region would exceed the speed of light. So it's a real frustration there. Clearly, we know that new physics is happening, physics well beyond classical general relativity is happening at the center of a black hole, but we can't see it because of the event horizon. And probably the only places in the universe where there are singularities now are the centers of black hole. But of course, if you trace the evolution of the universe back to the Big Bang, then we may have well, the universe may have well been essentially a singularity at the earliest possible times. Well, now, of course, we know, and I've already shown this once, that we can actually probably directly resolve the event horizons of these black holes. So these things really seem to exist, and it really seems to be that no matter how bright the material gets around the black hole, there really is a dark region in the center of the black hole from which no light is escaping. It's wise to be cautious when you're doing science. So I would note that these observations are not definitive proof that this is a black hole, but certainly whatever you need to explain this, it is consistent with a classical black hole, and you need something which, despite matter accreting onto it at an enormous rate, actually manages to not be very bright in the center. Okay, so speaking of which, although I have talked about the fact that black holes are real, black holes have event horizons, matter will cross that event horizon. Of course, it's not a solid surface, matter falls towards black holes, will cross the event horizon, we shouldn't see any light. In fact, accreting black holes, those down to which lots of material is falling, are amongst the most luminous objects in the entire universe. And it's those accreting black holes which form a large focus of a lot of my research. So what's happening in an accreting black hole? So here's a schematic. Of course, this is an artist's impression, although, as you'll see in a moment, we don't really need any deep theory to believe that the jets exist, because we can directly see them. But essentially what is happening, we know that in the universe, everything has some angular momentum. And if you have material falling down towards a central point, then all of the other components of angular momentum through collisions and interactions will essentially cancel out until the matter settles down into a thin disk with one remaining angular momentum vector, slowly loses angular momentum and energy as it drops itself down in a sequence of circular orbits towards the central object. So this structure is a thing that we call an accretion disk. Now, the amount of potential energy which is released as something falls down towards a gravitating object is essentially given by the density. It's given by the ratio of the mass over the radius. So the more compact you make something, the more energy you get as you drop stuff down in this accretion disk. And the highest ratio of M to R you get in the universe is with black holes. And in fact, this ratio is the same for all black holes. The radius of the event horizon of a black hole scales linearly with its mass. So what we see then is that we see material falls down towards black holes, it spirals in these accretion disks. And because this ratio is so high for black holes, huge amounts of gravitational potential energy are liberated here. So even though, in fact, if you're on a circular orbit just above the event horizon, you've only actually released half the gravitational potential energy that was available, that doesn't matter. You've released so much of it by dropping down so close to the event horizon that these things shine extremely brightly. So although the black holes themselves are dark, the matter around them, as it's falling in towards them, as it's accreting, can become extremely bright. Now, there is this other phenomenon. There's this phenomenon of jets away from the black holes, which has actually been known for a century now, and which we truly don't really understand very well, but which we know actually carries away a huge amount of energy. So I've mentioned a few times that matter is falling down towards the gravitational potential of the black hole. As it does so, it releases gravitational potential energy. That turns into the heat, which essentially becomes black body emission here and generates radiation that we see. But somehow that accretion energy also powers these relativistic jets. And we know, in fact, from doing pretty good estimates of their power, that they carry away huge amounts of energy. And as I say, it's a little bit of a mystery. We don't know how they form, but we know that nearly always when you get high accretion rates onto black holes, you see these things. So let me just prove to you that you can directly see them. So if you focus first on this sequence of images in the lower right-hand panel, this is a sequence of images of a binary system in our galaxy, which may well contain a black hole. There is actually a small possibility it contains a neutron star, but the phenomenon is the same. This number you see ticking in the top right-hand corner of the animation, this is day number. This is a sequence of daily images, and you can clearly see, I mean, the central binary is here in the center. You can clearly see that matter is flowing away from the central probable black hole. What's more, it's also the angle is changing and the jets are precessing with a period of about half a year on the sky. It's truly a remarkable object. These are a sequence of radio images, and it's usually radio telescopes we use when we're doing these studies of jets. And that's because the emission process which dominates the emission from these relativistic jets is the synchrotron emission process. So let me just finish off what it says in the top right-hand corner here. We've made estimates of the power in these jets, and it's about 100,000 times the total power output of the sun, for example. So there's a huge amount of power coming out in these jets. So as I say, we know that the emission that we're seeing, because of its spectrum, polarization, and other properties, is synchrotron emission. Synchrotron emission, as you know, is when you have relativistic electrons spiraling around magnetic field lines, and because they're spiraling, they're accelerating, and they're producing radiation. And given the magnetic fields and energies associated with most of these astrophysical sources, that synchrotron emission is very easy to see at radio wavelengths. So here you see a picture of a few of the antennas of the beautiful meerkat radio telescope array in South Africa, which is a telescope which we've been using a lot here over in Oxford. And I'm just going to talk through a couple of projects that we're doing to observe jetted sources with the Meerkat radio telescope here in Oxford, before I get onto the specific topics of neutrinos and gravitational waves. Oh, I should say that, you know, I already mentioned that we really don't know how these jets are formed, and people are trying very hard to understand, using very complicated numerical simulations, how these jets are formed. So what I'm going to show you when I press play on this movie is a general relativistic magneto-hydrodynamic simulation. So that is, you have particles and magnetic fields evolving in the metric, in the space-time around a rapidly rotating black hole. Now, in fact, people know how to do this. People know how to calculate this. And a lot of the issue right now is actually being able to optimize code so that you can run it fast enough such that it's realistic. So one of the issues here is that you need to run these simulations for millions and millions of orbits around the black hole before you might hope to settle down into a steady state, which is similar to astrophysical phenomena, which we see. And I would say there's no, you know, you can't really answer in one line why these jets emerge, but they seem to be just some emergent phenomena from the rotating general relativity. So this is a real simulation. There's a rotating black hole down here in the green region. The green and blue region here is a precessing inner accretion flow around the black hole. And the red and yellow material is material which is firing away from that central black hole. So you can see that this particular simulation has been designed to try and reproduce jets which change their angle on the sky, like the ones I was just showing you. So what is very clear is that when you run these simulations, if you have magnetic fields and particles in a rotating GR metric, then you can produce the jets. We still don't know, we can't measure properties like radiation and internal energy well enough to know whether these jets really correspond to the ones that we see, but we do see that it seems to be a natural property of these rotating black hole systems that you should produce the jets. Okay, so one of the projects which we're running here in Oxford is on the Meerkat telescope, is called MIGHTY. And this is looking at the cosmic evolution of supermassive black holes. So Meerkat is an extraordinarily sensitive telescope, but it also has a very wide field of view. So this is part of one of the deepest images with Meerkat of the sky. So this is a radio image. So you might think, looking at this, that this is an optical image of perhaps a globular cluster or something, but it's not. This is a radio image, and pretty much every single point you see on here is a distant radio galaxy. And that radio emission is produced either by star formation, supernova remnants, etc., or by powerful jets from active galactic nuclei. And if you look closely, you can see a number where there are clear doubles. So there's one here, there's one here, a beautiful one with bent jets, there's another one here with bent jets, and there's one here with more linear jets. They're all over the place. Essentially what we're doing is we're looking at the activity of supermassive black holes producing powerful relativistic jets at high redshift over cosmic time, and we're investigating how that might affect the evolution of galaxies over time. So if you zoom down on one of these objects, it might look something like this. Here's a central black hole. This is an image now on a scale of about the size of an entire galaxy. You can see a relativistic jet, highly collimated, coming out of one side, and you see diffuse powerful radio lobes on both sides. Now, the reason there's a little niche feature here, the reason that you don't see the jet coming in the other side, it is there, but it's a property of highly relativistic flows. When things are really moving highly relativistically, then you only see them if they're actually moving relatively towards you. And that's because they tend to beam their radiation forwards in the direction of motion. So the jet on this side is moving away from us, and we essentially can't see it. But the lobes themselves, the lobes are essentially, once the jet has decelerated and deposited all its energy in the surrounding medium, they're not moving at any particular high speed, and we can see them on both sides. If you zoomed in on this jet down close to the black hole, so the black hole is now here, then you can see a very interesting structure. We can see the region where the jet is first being formed. It appears to be brightened on the edges with a relatively empty region in the center, and it's extending directly back down towards the black hole. And again, sorry to get repetitive with this image, but it just so happens that what I've been showing you is M87. And if you zoomed in on that by about, so this zoom in here is a factor of 10 million. This zoom in here is a factor of 100. And we know now that there is the black hole right at the center where the jets are connecting directly to it. Something pretty small, as I've said, something about the size of our solar system and extending to something the size of an entire galaxy. It's really extraordinary. Now, we know that the jets from these supermassive black holes have regulated the growth of galaxies over cosmic time, and they really are some of the most important physical processes that have shaped the growth of our universe. And people who are doing large-scale numerical simulations of the evolution of the universe are really finding now that they need to incorporate kinetic feedback from these jets, otherwise they can't grow their galaxies properly. One of the more extraordinary images which we've produced with Meerkat, this is an image that was produced by my colleague Ian Hayward, is of the center of our own galaxy. So this is the central few degrees region of our own galaxy. This is a real radio image produced by the Meerkat radio telescope. The strongest radio emission is red. The Sagittarius A star, the black hole at the center of our galaxy, lives here in the center. And you see this extraordinary diversity of structures. So some things we think we understand. There are relatively spherical structures, such as this over here, which we think are probably more or less normal supernova remnants. So a massive star has exploded, you end up with a supernova remnant. We're relatively familiar with these. But there are these extraordinary long, thin, narrow filaments, and genuinely, we have no very good idea what these are. I mean, this image has been in the public domain now for over 2 years. The world's best and most ambitious theorists have looked at this, and no one really knows what these filaments are. It's truly extraordinary. They're very bright. This is pretty much all synchrotron emission. So these are relativistic electrons in magnetic fields again, but we just don't know what they are. You zoom out to larger scales, this is the same image, but zoomed out. You can now see that there were hints of an edge brightened structure on the zoomed in image, but now you can clearly see that there is evidence for large scale bubbles above and below the galactic plane away from the center of our galaxy, which really suggests the injection of lots of energy on a timescale of about 1 million years ago. What we're not sure about at the moment is whether or not this was because a relativistic jet switched on from the black hole at the center of our galaxy, or whether this was perhaps a prolonged episode of production of supernovae, which kind of produced a kind of amalgamated bubble of outflowing material. But whatever it is, something extremely energetic happened at the center of our galaxy about 1 million years ago. And this really sort of connects the center of our galaxy to the other galaxies out there that we see that all have these relativistic jets. And there's even though the black hole at the center of our galaxy is relatively low mass, being only maybe 3 or 4 million solar masses, so that's about a factor of 1,000 less than M87, there's still good reason to believe that in the past it would have been much more active and producing bright X-ray emission and relativistic jets. And then the black holes that I study in most often myself are actually the lowest mass black holes. So these are things we call stellar mass black holes. These are black holes typically of around 7 times the mass of our own sun. They're the direct products of the evolution of massive stars. They're in binary systems, although frankly, the binary companion doesn't really matter very much. It's just an orbiting fuel tank. Otherwise, they behave very much like the active galactic nuclei. We have accretion disks and we have relativistic jets from them. Now, from stellar evolution arguments, it's estimated that there are about 100 million of these black holes floating throughout our galaxy. That's an extraordinary number. And probably, if you just distribute these through the volume of our galaxy, that probably means that there is a black hole within about 10 parsecs of the Earth. And that's about the standard deviation as well. So, it's entirely plausible that as close as the nearest stars, there could be a black hole floating through space. Obviously, it poses no particular risk to us unless it's on a direct collision course. But because it's not accreting very much, we just can't see it. So these binary systems, they only represent about 1 in 10,000 of this overall population that accrete enough material and become bright enough to see. When they do become bright, we see them as very strong transient to variable radio emitters. So this is a movie of a projection of our entire galaxy. So if you're not familiar with these projections, this is essentially projection of the galactic plane. The galactic center is right at the center here, and the galactic anti-center, that is looking from our point of view away from the galactic center, is at both of these edges here. And this is the north celestial pole, and this is the south celestial pole. And what you're seeing here is a compilation of about 2 years of data from a project which I co-lead. Every time one of these black holes undergoes an episode of episodic accretion, it produces small-scale relativistic jets. These produce radio flares, and these we pick up in our monitoring program with Meerkat. So this is just over a period of about 2 years, and you can see that during this period, there were already a good 10 or so active, powerful outbursts from black holes within our own galaxy. Now, some of these were black holes we'd known before, but a couple of these black holes, we had never been aware of their existence until they suddenly switched on. We saw the powerful X-ray and radio emission from them. So black hole jets are popping off all the time, even on relatively small scales, but still highly powerful and within our own galaxy. So let me put all these different types of black holes in some kind of context. And one of the ways that's representative to do this is to put them in the mass against accretion rate plane. So the mass axis, the x-axis, is the easiest one to explain. So the lowest mass black holes we know of, we refer to, as I've just mentioned, as stellar mass black holes. And they have masses of about 10 times the mass of our sun, and we understand how they're formed. A massive star of about 30 solar masses collapses, can produce a 10 solar mass black hole. The most massive black holes have masses approaching 10 to the 10 solar masses. M87 is one of these very massive black holes, so that's extraordinarily massive. The accretion rate scale I use here, I use accretion rate divided by Eddington. So probably most of you know of the Eddington rate, but the Eddington rate is the maximum rate at which something can accrete spherically, symmetrically, before the radiation pressure from the outgoing radiation from accretion would push back on the surrounding material enough that it would stop accretion. It's rather an idealized scenario, but in fact, we find that in astrophysics, it does appear in many cases to be a limit, although we will see that there are exceptions. And again, the lowest accretion rates that we find are things like Sagittarius A star at the center of our galaxy, where we know this ratio is less than about 10 to the 8. And there are exceptional objects where this ratio is much, much greater than 1. So the LIGO neutron star merger event, which produced a black hole, which I'm shortly going to come on to, had an accretion rate much, much greater than Eddington. The AGN at the highest masses and highest accretion rates are at about 1 here and about 10 to the 9 solar masses here. There are things called tidal disruption events, which I'll come on to shortly, which are relatively intermediate mass supermassive black holes, if that makes sense. The X-ray binaries I study are exactly the same mass range as those produced by the merger of 2 neutron stars, but are accreting at a somewhat lower rate. And this is also the same mass range as the individual isolated black holes that LIGO first discovered in 2015 as merging sources producing gravitational wave bursts. And as I say, the tidal disruption events tend to have around the same mass of central black hole as that observed at the center of our own galaxy. Okay, so let's go beyond photons then. Let's go into the multi-messenger astrophysics. So the first of the 2 case studies I want to describe is the connection to gravitational wave sources. So in 2015, as I've mentioned several times already, gravitational wave bursts were discovered by LIGO from merging black holes. Several good, convincing examples of these were found over the following years. But we all knew that hypothetically, we could also get gravitational wave bursts from merging neutron stars, or also from the merger of a neutron star or a black hole. One of the reasons this was so exciting is that when 2 black holes merge, if there's no other matter around to be perturbed by this, then there's going to be no electromagnetic radiation. You're going to have something that's extremely dark, the darkest thing in the universe, merging with another thing that's equally dark. There's going to be no photons produced. So we're not going to be able to do any kind of cute tests of the speed of gravity against the speed of light. But when neutron stars merge, there is matter ejected, and there should be good reason to expect electromagnetic radiation. So that's what people were waiting for. So as I said, the event I'm going to talk about here, this is at the lowest possible end of the black hole mass range, and at the highest possible Eddington ratio. So this is really the top left-hand corner of this parameter space. So this figure here, this shows you the distribution of black hole and neutron star masses on scales lower than those found at the centers of galaxies. The x-axis means nothing really. It's just been created so that you can spread these points out and make it look more visually appealing. So let's start with the black holes that we knew before. So the black holes that we knew before are the ones in purple, and these are in the binary systems that I spend a lot of my time studying. LIGO by 2017 had observed 5 black hole mergers, and in each case, these are the 2 black holes which were measured, which had their masses measured prior to the merger, and after the merger, you got this resultant black hole. So these were all similar masses, but a bit higher masses. These yellow points here were all the masses of known neutron stars, and typically these were neutron stars whose masses had been measured because they were pulsars, or again in binary systems. In 2017, as I've mentioned, LIGO measured the merger of 2 neutron stars into a black hole, we think, of a mass probably around 3 solar masses. So this may be the lowest mass black hole ever discovered. Unfortunately, because of the frequency range limits of LIGO, the actual moment of merger was not observed. We don't know for certain that a black hole was formed. You know, general relativity doesn't really allow anything else. I love this movie. This is a movie showing you the kind of smooth version of the signals which LIGO had detected up to the point at which the neutron star merger was detected. So what you're going to see on the x-axis is a time range, and what you're going to see on the y-axis is the amplitude of the gravitational wave oscillation detected by LIGO. The bottom event is GW170817, and the top 5 were the known black hole mergers event, and the x-axis is in seconds. If you watch this movie, you see that all these black hole events, they were all over in about 2 seconds. So people knew by then what these black hole events look like. Now, the reason that events have a finite duration is that LIGO has a fixed available frequency range in which it's sensitive to gravitational waves. When something moves into that frequency range, it starts getting detected. And when it moves out of that frequency range, or in the case of black holes, when they finally merge, then it's no longer detected. The rate at which it moves through that frequency range is basically proportional to the rate at which it loses gravitational energy. And that's proportional to the rate at which you're swinging mass around. And of course, these black holes are essentially swinging about 40 solar masses worth of mass around. So they evolve through this frequency space very, very quickly. In other words, they coalesce very quickly. This signal looked nothing like it. Look, this signal is still going on a minute later. And you heard a little chirp there, which was the sound as the neutron stars just came together at the end. So that signal went on for about 60 seconds. It went on for a minute, and that's because the rate at which you're losing the gravitational radiation is much, much slower in this event. So you could immediately tell that these were neutron stars merging, and that rise in frequency right at the end was as we found the neutron stars just about to coalesce, and then we lost them. So there was an extraordinary, you may have heard about this before, but there was an extraordinary global effort to find the electromagnetic counterpart to this event. I've never seen anything like it. There was every single telescope in the world that could looked in the direction of this telescope, of this gravitational wave event. So this is a projection of the celestial sphere. The dotted green region here represents the region of localization from LIGO. Now, fortunately, the event was also detected by the European gravitational wave detector Virgo, which reduced the localization region here. Now, 1.7 seconds after the gravitational wave burst was detected, a gamma ray burst was detected, which is a flash of gamma rays in the sky. And this was localized by 2 different mechanisms. One is the interplanetary network. So this is a network of deep space spacecraft which have kind of as a tertiary instrument something that can detect and triangulate gamma rays. It's not very good at triangulating, but it's better than nothing. So that was this blue strip, and then there was a gamma ray burst monitor on board another telescope which localized it to this region. So the overlap of those 2 basically gives you this shaded hemisphere here, and it's smack bang on top of the gravitational wave localization. So there was almost certainly the gravitational wave was associated with this gamma ray burst. Within this localized region, there was something like 50 galaxies. Given that the gravitational waves, they also actually give you an indication of the distance. So it's not just an area on the sky, but it's a volume in space. There were about 50 galaxies. Every single one of these galaxies was observed by multiple optical telescopes, and about 12 hours after the detection of the gravitational wave, a new source which hadn't been there on any previous images was detected. So this is a galaxy called NGC 4993. It's at 42 megaparsecs. On a cosmic scale, that's pretty nearby, and this thing here was new, right? This was the optical counterpart associated with merging neutron stars. Well, this was extraordinary. This was very, very exciting, but did this thing produce a jet? So those of us who work on these relativistic jets, we were very, very curious about this. Well, the answer is it did. So what I'm showing you now is I'm going out to much longer timescales. I'm going out to nearly 1,000 days. And what you're seeing here is a compilation of all the observations that were made by radio telescopes all around the world of this source. And in addition, at X-ray energies by the Chandra and XMM X-ray telescopes. And again, we're observing at radio wavelengths because the synchrotron emission associated with these relativistic electrons, which makes up the bulk of the emission of the emitting particles from these jets, emits in the radio band. But it turned out these electrons were accelerated to such high energies, to TeV energies, in fact, that they were also emitting in X-rays. So this radio afterglow, most unusually, actually, for these phenomena, it didn't peak early and fade away, but it rose very, very slowly. And it peaked at about 1 year. These are the same data, I should say, the top and lower plots. This is just has a running time average on it. The data, the radio light curve and the synchrotron light curve, I should say, peaked at about 1 year. It's slowly fading away. And observations are still taking place to this day, nearly 5 years after the event, to see if the very late time evolution of these ejecta can be detected. This again remains a unique event. No one's ever seen another electromagnetic radiation and gravitational wave burst. All the indications were that this probably came from a jet, but there were alternative theories. But again, incredibly, using the very highest angular resolution radio observations, so using a technique known as VLBI, very long baseline interferometry, it was shown that between day 75 and day 230, so that's about here to here, this is a log scale, the locus, the core of the radio emission actually moved. And it moved in such a way that it proved that all of this radio emission was coming from a relativistic jet. So this neutron star merger event, which is the first electromagnetic radiation gravitational wave event, produced a relativistic jet of the kind that we find from black holes on all different scales around the universe. Probably what happened, the latest thinking of what happened is something like this. There was a jet produced by the merger of the neutron stars. It had an opening angle of about 5 degrees, but in fact, the beam of the jet was probably offset from the line of sight directly to the Earth by somewhere about 14 to 28 degrees. And this means that the observed luminosity, so I've made a very simplified sketch here of what happened. So the observed luminosity of the jet is a convolution of two effects. So see if I can explain these to you. One is that the jet is launched with a certain amount of energy. As it propagates away from the black hole, it's pummeling into the interstellar medium and it's decelerating, it's losing energy. As it does so, it heats up a bit, but ultimately over time, its intrinsic luminosity will decrease. And that's essentially friction with the interstellar medium. However, the net Doppler factor of all of the jets, so the jet has a finite size, so I'm going to say net Doppler factor. The net Doppler factor of the jet actually starts off as a number less than 1, peaks, and then falls off again. And I'll try and explain that in the next slide. And the convolution of these two effects means that you get something that very slowly rises, peaks, and then fades away again. And I think that's what we saw. The total energy in the kinetic energy associated with this event was around 10 to the 50 erg. So that's 10 to the 43 joules. That's close to the amount of energy that's released in a supernova explosion. So when we're trying to understand the real physics of what happens in these mergers, we need to really understand that, you know, a large component of the energy budget is the kinetic energy which went into producing this jet. So let me try and explain to you this Doppler effect then. So when something's very, very highly relativistic, you see the emission only along the line of sight. Now, as I said, the jet wasn't pointed directly at the Earth, and initially only things in this blue cone would have seen a positive Doppler factor. For everything else, the jet would have seemed fainter than it intrinsically was. And this, at early times, the Lorentz factor was greater than 10. At sort of medium times, the Lorentz factor would have dropped to about 2, and there is still beaming, but the Earth has now, us and our telescopes on Earth, we're now within the beaming cone of this radiation. We now can see the jet. And in fact, as we see more and more of the jet, as we see the whole width of the jet appears to get brighter and brighter. So as we move from this stage to this stage, then the jet is appearing to get brighter and brighter. Even though it's intrinsically fading, we're actually seeing more of it because the Doppler factor towards us is actually increasing. And then at some late stage, when it's essentially decelerated to a stop, the emission becomes more or less isotropic, and then the energy losses as it loses luminosity with time dominate, and you see a fading emission again. So to summarize then, GW170817 produced a neutron star merger. It produced gravitational waves, and it produced a gamma ray burst. Something I didn't mention, but which was very exciting, which was the arrival of gravitational waves and electromagnetic waves within 1.7 seconds of each other from a distance of 42 megaparsecs means that lots of exotic theories of gravity were ruled out. Anyway, we know that this event produced a highly relativistic jet that was slightly misaligned to the line of sight to the Earth and had a lot of energy produced within it. So the results I've been showing on this source are from Mooley et al. And Macatini et al., but there are many, many other papers on this source. All right, let me wrap up then with the final angle of multi-messenger astrophysics, which is the connection to neutrino sources, and was in fact the original reason which I think I caught the attention of your organizers. So tidal disruption events, as I've already said, they sit in sort of intermediate mass range, and they briefly go through phases of very high accretion rate, which means that they get the strong accretion disk and the relativistic jet. So there was a paper last year published in Nature Astronomy. In fact, it got the cover of Nature Astronomy, which is one of those little prestige markers in research. It doesn't really mean anything for your career, but it's very nice, which is with the capture and new source of neutrinos. And in summary, the paper was about the possible detection of a 200 teravolt astrophysical neutrino coincident with a strong jet from a late time tidal disruption event. Now I'm going to show you a movie in a second of what we believe is going on in a tidal disruption event. The whole story is quite exciting. The neutrino was detected by IceCube, which is down at the South Pole. And the IceCube detection prompted an optical survey facility, which is called the Zwicky Transients Facility, to look for an optical counterpart. And in fact, the Zwicky Transients Facility, or hereafter the ZTF, actually realized that it had already discovered this tidal disruption event, and you could make a clear association between the two. All right, if you'll forgive me, I'm going to show you a small movie from the initial press release about this, which shows a simulation of a tidal disruption event. Unfortunately, perhaps fortunately, it's accompanied by rather dramatic music. But the idea is essentially that a star falls close enough to an intermediate mass black hole that the tidal forces on the star pull it apart, such that half of the star is essentially accreted towards the central black hole, half of it is unbound from the system and ejected, but this torn apart material dramatically increases the accretion rate onto the black hole. So my apologies for the dramatic music, but there you go. Maybe it adds a bit of atmosphere. I believe that's the star being torn apart. There you go. So the star goes on a close orbit of the black hole and is essentially torn apart. This results in very dramatic accretion increase onto the central black hole, which produces results in the production of these jets at a high accretion rate. A beautiful movie, but of course, as we know, as we know from the images of the center of our galaxy, the real astronomical data of things like this, when you look close enough, actually does look that beautiful. So I'm not an expert on IceCube, but it is a really remarkable facility. So IceCube is a laboratory near the Amundsen Scott South Pole Station in Antarctica. And in IceCube, strings have been dropped by melting down 2.5 kilometers into the ice. And each of these strings contains along it large numbers of these digital optical modules, which are essentially photomultipliers, and neutrinos can cause streams of flashes as they move through the ice, which can be picked up by these photomultipliers. Absolutely extraordinary, I think. I mean, strings going down sort of, 2.5 kilometers into the ice, large numbers of them below the Antarctic ice. Extraordinary. IceCube has discovered a large number of neutrinos, a large number of which appear to be astrophysical, and there's good reasons to think that a large number of these are associated with relativistic jets from active galactic nuclei, but the connection's not really proven very well yet. So IceCube detected a neutrino called IC 191001A. And this particular, so they give individual neutrinos names. They're that infrequent. The arrival time of this neutrino is marked with the vertical dotted line on this graph, which I'll return to in a moment. They have a number of criteria for estimating whether or not these neutrinos are likely to be astrophysical, and they estimated this had a 59% probability of being astrophysical. The thing is, it seemed to be associated with this tidal disruption event, both temporally and position on the sky. Bright tidal disruption events are quite rare events, and the combined probability, an estimate of the combined probability of both an astrophysical neutrino, or this neutrino, and the TDE was made to be about 0.2%. So it was considered this was a very likely association. So what you see here on the top panel over a period of about 250 days is an optical light curve. So this is the optical flux as measured by the Zwicky Transient Facility and other facilities. The neutrino was detected at this point, at which point Zwicky looked back in its archives and found that actually there was an event which had started about 170 or 180 days earlier, had peaked about 30 days earlier, and showed all the characteristics of a tidal disruption event. So it seemed that there was a tidal disruption event that was associated with this neutrino. However, tidal disruption events are, you would think from first principles, or perhaps not that naively, that, they'd be doing their most energetic stuff early on, when the accretion rate was highest. So what was still going on at 170 days that could be associated with the production of a neutrino? Well, what we found, and my team was involved in this, that we started observing this source in the radio band, and actually the radio evolution was very unusual. Now, there is a large diversity of individual radio behaviors. This radio behavior is nearly always associated with these jets, but often you see a single event that essentially evolves with time in a very simple way, like you did for the neutron star merger. However, the behavior of the radio emission from this event was a little bit different. So these are a sequence of broadband radio spectra, which we and other teams compiled for this source. And we saw that as time went on, so this is 42 days, 70, 120, and 178 days, you could always see a peak in this synchrotron spectrum. What this peak allows you to do, you can make the assumption that this peak is due to self-absorption. There's a few equations which you can relatively straightforwardly rearrange. And what you can do is you can get the size of the emitting region from this. And you can also get the internal energy. So at 4 epochs, we were able to measure the size and the internal energy of this jet. And what we found was that the internal energy of this jet was rising. Right now, if you fire off a single blob, like in the neutron star merger event, the energy decreases with time. You inject it at the start and it loses energy. So, that's the way things go in the universe. But in this one, the energy was rising and its size was rising such that it seemed to be propagating outwards with a mildly relativistic speed of about 0.12 c. So the best explanation for this increased energy input is actually that the black hole was actively still firing energy into a jet. So rather than have fired off a blob and stopped, actually there was a jet had been continuously injecting energy for at least half a year. And you'll see that this time here, 178 days, actually corresponds to around the time when the neutrinos were detected. So unusually in this source, a lot of power was still going to the jet, particle acceleration was still going on at the time when we detected the neutrino. So that lends a lot of support to this scenario that you know, some strong, some high energy processes were going on in that jet. Now, one of the nice things about trying to understand what processes go on in these jets is you want to know whether or not relativistic or high energy protons are involved. A lot of theories of jets, you know, invoke the presence of high energy protons. The trouble is that, you know, high energy protons can produce gamma ray emission, but there are other ways of producing gamma ray emission. You can get gamma ray emission directly from very high energy synchrotron emission or from other processes like inverse Compton emission. But if you see neutrinos, that's direct evidence that high energy protons were involved. And you can see some of the particle decay chains essentially that lead to the emission of the neutrinos which were detected. So it looks like the neutrino associated with this TDE, with the name 2019dsg, the one I've just been talking about, that probably is the smoking gun, perhaps for the first time, of hadronic processes involving protons directly in a relativistic black hole jet, which is very cool. All right, so I'm near the end. This is my penultimate slide. So this neutrino, if astrophysical and if associated with this TDE, then it's almost certainly associated with this very powerful relativistic jet from this TDE. As I said, the radio observations, which my team were involved in, they reveal strong energy injection for at least half a year after the initial event. And the particle acceleration was ongoing up to at least the time of the neutrino detection. The jet probably, I'm no particle theorist, but the jet probably provides a plausible environment for proton-proton or proton-gamma hadronic interactions, which could have produced the neutrino. So it is plausible that the neutrino was produced there. And in fact, it could be that TDEs could be contributing significantly to the overall astrophysical neutrino flux. On the other hand, that does raise the question, why would they be doing this more so than other active galactic nuclei, of which there are many more and which are much more powerful. And everything I've shown you here comes from a paper by Stein et al., which was published in Nature Astronomy in 2021. All right, I will wrap up there. I've given you a whistle-stop tour of relativistic jets from black holes and how they seem to be connected to all of these black holes in different environments and how they've been, you know, intimate components of both a gravitational wave source and what appears to be a neutrino source. Well, first off, as I started, never forget that black holes, they seem to be everywhere in the universe, but they're really bizarre. Always stop and think about this. You know, they are like nothing else in the universe, and yet they seem to be everywhere, and they seem to be very important players in the evolution of our universe. They ubiquitously produce powerful jets which shape their surroundings, and they are the sites of some of the highest energy processes and most relativistic bulk flows in our entire universe. They're essentially these high energy physics laboratories floating around the universe. The LIGO-Virgo burst GW 170817 was an electromagnetic was also an electromagnetic source, and it produced a powerful relativistic jet. And the Tidal Disruption Event 2019dsg was also a powerful relativistic jet source, and in this case it likely produced an astrophysical neutrino, which is still a field really in its infancy. And I will stop there and thank you very much for your attention. Thank you.
Thank you so much, Professor Rob Fender, for the wonderful talk. Now let's move on to the questions. So if you have a question, you can either use the Zoom's reactions function to raise your hands, or you can also put it down in the chats. Professor, feel free to take any of the questions that comes along.
I see one in chat that says, are short gamma ray bursts a typical characteristic of colliding neutron stars? Okay, this is a very good question. So for a long time, so gamma ray bursts are these flashes of gamma rays in the skies, which have been known for a long time. In fact, some of you may be aware of the story. They were first detected in the 1960s by satellites, which both the US and Russia had launched to check on each other, that each other were adhering to the Nuclear Test Ban Treaty. But in fact, they found flashes of gamma rays, which could have been signatures of atomic weapons, but in fact coming, from the opposite direction, coming from deep space. What we know now is that gamma ray bursts occur both in short and long forms, and the short gamma ray burst lasts about 2 seconds. The long gamma ray burst can last much longer durations. So because there are two classes, people have hypothesized for a long time that there might be two physical origins, and it's been suggested that long gamma ray bursts are associated with the collapse of a massive star, and there seems to be some tentative evidence that some long gamma ray bursts are associated also with supernovae, which seem to confirm that association. So it had been suggested for a long time, both from the timescales involved and also from the rates. So, you can do long-term simulations where you can estimate how often neutron stars should merge. It had been suggested that all short gamma ray bursts were associated with merging neutron stars. I know one event doesn't confirm an entire hypothesis and population, but I think most people are taking it now sort of via Occam's razor that given that we've seen one definite example of a merging neutron star and it was associated with a short gamma ray burst, that, it's entirely plausible that all short gamma ray bursts are merging neutron stars, yes. I don't see any hands raised. I'm not sure if I would see everybody.
I'm not seeing them on my end as well. So maybe a question from myself. You've shown the image of the structure of a galaxy with all those tendrils. So, and that we don't quite know what's forming them, but are there any hypotheses as to what they could be?
Right, so you're talking about the center of our galaxy.
Yeah.
Yeah, that's just extraordinary, right? This image.
Do we have any clues on what could possibly be doing all that?
It's a very good question. So let me emphasize what we know. So if you look at them, they're long, they're thin. It's very bright synchrotron emission. There is some suggestion that this larger structure, which seems to come out from the center, has these along the edges, but we also see some which are not along the edges, and we also see some which are at completely different angles to the flow. So there are two hypotheses which have been suggested at the moment. One is that this is some kind of plasma process. You end up with ropes, plasma ropes, which somehow produce a concentration of magnetic field, which enhances the synchrotron emission. I'm not personally sure or convinced about the physics of that. I'm staring at the image now, trying to see if I can see on this one an example of the other hypothesis. I don't think I can, but there is a suggestion. So of course, we know that the center of our galaxy is likely to have large-scale magnetic fields in them, and probably these filaments do trace the magnetic fields at the center of our galaxy. On the other hand, why should only some of them be bright? So one suggestion is, we also know that there's lots of neutron stars and other high energy objects in the center of our galaxy. One suggestion is that every now and then, one of these neutron stars will just produce a burst of high energy particles. And as it does so, because this is a highly magnetized region, those particles will essentially just stream along the nearby magnetic field line. The neutron star will then move on. These things tend to have, space velocities. They tend to move through space. So you're just left essentially with this string of particles, which is tracing out the local magnetic field. But the source of energy that injected the electrons has a finite duration and is gone. There is some circumstantial evidence for that. I can't find any examples in this image, but there are some cases where you see one of these thin filaments, then a little bit further along you see another one, but not so long, and you see another one that's even shorter. So you've got like a triangular shaped fan. So you can imagine that there was a neutron star here a long time ago, fired out some stuff, stopped, carried on moving in that direction, fired out some more, stopped, carried on that direction, fired out some more, stopped, and possibly that's an explanation.
Right. Thank you so much for the answer.
The mass and spin of a black hole presumably change as it accretes. Can we therefore ever know exactly what the two values are? This is a very good question. If a black hole is limited by the Eddington rate as to the rate at which it accretes, now we do know, of course, that in some cases, such as gamma ray burst, you massively exceed the Eddington rate. But in the case where a black hole is accreting at the Eddington rate, you can actually do a fairly straightforward calculation of how long it would take to exponentially grow in mass. And it's a thing called the saltpeter time. And it's a few times 10 to the 7 years. So actually the rate of change of mass is actually relatively slow. And the rate of change of spin is pretty much as slow. So over cosmic time, these black holes certainly grow and their spin evolves, but on the timescales over which humans make observations, these mass and spin, they really don't change very much. And of course, it must have been accretion essentially over a Hubble time over the entire age of the universe, which allowed the most massive black holes to grow to the size we see them today. Even encapsulating the whole of human astronomical history, then no particular black hole has probably changed its mass or its spin very much. I don't think I see any other questions in the chat.
Right. So if there are no more questions, I guess that will be it for tonight. Thank you so much to everyone for attending the talk tonight. And thank you again, Professor Rob Fender, for giving a wonderful sharing. This will be the last talk of the term and as well as the year. So we look forward to another series of wonderful talks from more speakers next Michaelmas.